So, all right, let me restart. So again, I'd like to thank the organizer for inviting me here. So this is my first time in Korea, and it's been a great time, and I very much enjoy the meeting as well. So I'm going to talk today about our work on non-adiabatic statistical theory package. Basically, this is something which I promised, I think, 2 years ago, what we will implement. So now it's implemented, so it's actually available online. And the reason we do that, is because we want to know, we want to study basically spin-dependent processes, and specifically kinetic and dynamics of those spin-dependent processes. So first of all, what do we mean by spin-dependent processes? There are different names basically, but we heard yesterday talk from Miguel, in fact, about this particular complex. So this is an example of intersystem crossing, right, from excited states through manifold of different spin states, and kinetics, or how fast those transitions occur, are actually very important for various applications. You don't need light basically to initiate intersystem crossings or transition between different spin states. So that can be done thermally. And this is an example on the right of the binding of oxygen or carbon monoxide to hemoglobin. So that's actually very common reactions when small molecules bind to the transitional metal complexes, and that's accompanied by change of the spin states. Also, in this case, you go from high spin state to low spin state, basically. I'm involved with chemical physics program at UNR, at University of Nevada, Reno, where I'm from. And there is a lot of collaboration with the physics colleagues going on. And one of those are related to spin coherence in alkali metal atoms trapped in parahydrogen matrices. So those applications are important for, those systems are important for quantum information applications. So we can use them as qubits basically. And again, we're interested in things like spin relaxation, spin decoherence there. Also, it's a relatively recent project now. It's a big actually efforts funded by DOE nowadays. So we involve multiple experimentalists. Also at our university. So that's where we're working on the molecular magnets. And again, we're interested in relaxation of magnetic properties in those systems, and which related to the spin relaxations. So how do we study those kinetics? So the kinetics and dynamics basically here means effectively the rates of transitions between different spin states. If we have rates, we can actually predict things like branching ratio, quantum yield, lifetime of excited states, and so on. And we use two different approaches to do that. Non-adiabatic, in our case, we use direct molecular dynamics, and I'm not going to talk about that in any details because today I will be focusing on non-adiabatic statistical theory. The difference between those two approaches are what in dynamics, basically, you need, I mean, this is multidimensional, of course, approach. So you explore entire potential energy surfaces, but the problem is you need usually tens or hundreds of thousands of electronic structure calculations to do anything useful in terms of predicting the rates and so on. In statistical theory, the idea is it's basically, in a sense, generalization of transitional state theory. So we're looking at the crossing point between the two spin states. We call it MECP, or minimum energy crossing points. And all we need is properties at this minimum energy crossing points, which include things like density of vibrational states and spin orbit coupling, which is main coupling basically between different spin states. And we also need like usually properties at reactants and products, especially if you want to predict forward and rate and backwards rate constants. So now, why do we care about non-adiabatic statistical theory if we can do non-adiabatic dynamics, basically? So we heard several talks already, and I think there are another one coming by Mario Barbati at the end of the day today. So this is how I think in terms of the time scales versus system size, which we can simulate either with molecular dynamics, non-adiabatic molecular dynamics, or non-adiabatic statistical theory. So you can see what in horizontal sort of axis we have a time scale. And molecular dynamics certainly can access things in picoseconds time scale, maybe a little bit longer, maybe up to nanoseconds. We can look at the system size of maybe 100 and maybe a little bit more atoms, but that's pretty much the limit. So again, we might hear today from Mario later in the day, so how to extend the time scale, but nevertheless, this is probably as far as we can go nowadays. And that's, again, the limitation here comes from the number of electronic structure calculation you have to do. So with non-adiabatic statistical theory, we can study much larger system, and which, in my opinion, actually probably even more important, we can study much slower spin-dependent transitions, basically, so which are not accessible with molecular dynamics typically. And this is only with time-dependent DFT, or, well, let's say something which has a similar price to time-dependent DFT, could be different methods. But usually you want, in order to predict kinetics accurately, you want some high level theory. So let's say if you start doing CASA-CF, now this triangle on the left starts shrinking, basically. It starts shrinking because, again, the electronic structure calculation are expensive. So for the same computational cost, you can do much less calculations, means what you can propagate molecular dynamics only for shorter period of time, and you can study small system only. So, and of course, even CASA-CF probably not a great ideas in many cases because dynamic correlations are missing here. So you want maybe something like CASPT2 or maybe Kapov cluster, and that's basically reduce the size of this region available for molecular dynamic simulation even more to the sizes of maybe a node of, like, the time scale become a node of picosecond basically, and the size and maybe a couple of dozens of atoms, and that's about it. So that's our motivation. So of course, a statistical theory has its own issues, right? So if you're interested in non-locality, if the process basically explore large part of potential energy surface during the relaxation, so you do need non-adiabatic molecular dynamics. So, and statistical theory is not a good idea because it's by definition it's effective one-dimensional theory basically, which consider the this reaction propagated along a single reaction path. Very fast femtosecond, picoseconds barrierless processes are probably better simulated with non-adiabatic molecular dynamics. So where statistical theory is much more suitable for slow processes. It also has to do with the statistical nature. So we want energy distribution among all the vibrational degrees of freedom, basically, and the longer the process, the higher the likelihood that you get more or less uniform distribution of these energies among different degrees of freedom. So the big advantage, again, as I mentioned, so in non-adiabatic statistical theory, you can use very often very accurate electronic structure methods, which become very difficult with molecular dynamics. And also important things are quantum effects. So quantum effects in many types of dynamics, not at all of them, but at least traditional surface scoping, usually doesn't account for things like quantum tunneling or zero-point vibrational energy. So, and that's something which can be accounted in statistical theory relatively easy. So now this is, I mean, I just told you what the applying statistical theory to small system is not a good idea. So, and this is the example of germanium H2. And the reason we look at this is because we want to compare our ab initio molecular dynamics. We use so-called ab initio multiple spawning technique, which is arguably significantly more sophisticated than surface scoping, but that depends on the basis set, of course. At any rate, so this is comparison of non-adiabatic dynamic with statistical theory, and we apply it to this tiny system. And there is actually a funny story behind it. So I remember when we picked it up, so several years ago with my postdoc, and my postdoc was very unhappy. So saying like, well, nobody cared about this molecule, so I never heard about it. So, and then after we published the papers looking at the relaxation, basically spin relaxation in the system, so a couple of years later, the experimental paper was published, and the motivation was, well, this system seems to be really interesting because theoreticians study that. Anyway, so at the bottom here, so we basically calculated forward and backward rate constant transitions between triplet, lowest triplet and singlet states. And dynamics actually, so we have a rate constant in the first and second row, and last row basically is lifetime of the triplet excited states. As you can see, so for statistical theory, we calculate probability of transitions, and I'll mention it on the next slide, how it works. So for with different type of approximation, like Landau-Zener, recoupling Drew-Nakamura, going from simple Landau-Zener to much more sophisticated Drew-Nakamura techniques. So, and therefore we get some spread of the lifetime. And in general, this lifetime from statistical theory is about like maybe 2.5 order of magnitude larger than the values from non-adiabatic dynamics, but still for a system of this size, it's actually, we were actually very impressed with it works that well. So And in fact, we did this simulation with the reason there are two papers there cited is because we did this simulation with DFT first and then with CASA-CF, and it turns out the difference between DFT and CASA-CF is actually more significant than difference between dynamics and statistical theory. So electronic structure actually very important. So it's often more important than the different approaches to predict the kinetics. So how non-adiabatic statistical theory works. So this is the sort of probably central equation. We have microcanonical rate here. So microcanonical rate written as basically, it depends on several quantities. There's rho, density of reactants. This is, and density of the, density of the rho vibrational states at reactants, and density of rho vibrational states at so-called minimum energy crossing point. Again, this is on the left. You can see this is a crossing sort of minimum on a crossing seam between different two different spin states. And transitional probability, again, so within the integral can be calculated either with Landau-Zener, more sophisticated weak coupling theory, which account for tunneling, or even more advanced Zhu-Nakamura formula, which cover the whole region, including the strong coupling, basically, between the different spin states. So this is how quad in generally organized. So what we need basically electronic structure properties or properties of the reactants and minimum energy crossing point from electronic structure quad. So we need for both of these points, we need moment of inertia, vibrational frequency. That's for calculating vibrational and rotational density of states. At minimum energy crossing point, we also need reduced mass. We need the spin orbit coupling, and for more advanced sort of type of application, we can also use reaction path polynomials basically for interpolating the reaction path. So, and on the right, so there are different ways to calculate probability of transitions, and then rho vibrational states, rho vibrational density of states, and probability of transitions get fed into the actual model, which calculates the rate constant, and we can get things like microcanonical rate constant, which is energy dependent. We can get thermal rate constant or canonical rate constant, which depends on temperature, and well, obviously things like probability of transitions and so on. So the code actually written in Fortran, so I'm talking about Fortran versus Python. We do have some configuration script written in Pythons basically, and I think there are some tools, computational tools. We also have pieces of Python code there, but mostly it's more than Fortran. We have set of automatic tests, which is useful when you change the code or you want to just to make sure you install it correctly, everything works. Computational tools are actually very important in this case, mostly for calculating so-called effective Hessian. So we need to calculate to obtain this rho vibrational density of states at minimum energy crossing point. We need so-called effective Hessian, which is a Hessian which represents the seam of the crossing between two surfaces. Basically, it's n minus dimensional seam, which is n is dimensionality of potential energy surfaces in this case. And typically, it's not available in electronic structure code, so you can calculate Hessian for each state in there, but then there are ways to combine those Hessian and actually also require gradients. And then you can calculate so-called effective Hessian and get the basically vibrational frequency on the seam. And actually reduce mass, which we also need to calculate the probability of transitions. So the input come from electronic structure code. So as at the top, I mentioned games, MoPro, QChem, ORCAR. So in principle, it's relatively easy to adapt to any other code. So probably effective Hessian calculation is probably most challenging part. So if it's not implemented, it has to be sort of implemented, but it's not actually very difficult. Input again from electronic structure comes in the form of energy gradients of the states, Hessians. So we need for vibrational density of states, moment of inertia, for rotational density of states, and spin orbit coupling to calculate the probability of transitions between spin states. In output, you basically get probability of transitions and rate constants. So again, so we can do forward, reverse rate constant, microcanonical, canonical rate constant, and so on. So this is an example of application where we're looking at the intersystem crossing in very small molecules. So this is the thiophosgene. And there are actually the reason we got interested in this system, so is because of this experimental value available at the bottom left part of the slide here. So I'm not going to go through the whole spectroscopy setup here. So it's actually pretty sophisticated experiment, which is take advantage of the symmetry of the excited states and sort of the fact that many transitions are forbidden basically by symmetry. So anyway, so the experiments produce the 23 nanoseconds lifetime for lowest triplet state. And the best theory, which tried to model the system based on Fermi-Golden rules, produced 0.02, 0.04 basically nanoseconds, which is 3 order of magnitude smaller. Means decay rate is like 3 order of magnitude faster than the experimentally measured. So at this point, we got interested in trying to figure out what's going on here. So, and try our theory basically and see how much better it works, hopefully, than Fermi-Golden rules. And this is just to demonstrate, I don't expect you to see all the numbers there, so in this small table, but this is just to demonstrate what kind of sort of the advantages, I guess, of non-adiabatic statistical theory in terms of the using high-level electronic structure methods. So here we've done anything from cup of cluster, single, double, triples with up to quadruple basis set, and CAS-PT2 with active space of 24 by 16. Basically, we can get very accurate electronic structure that's required for predicting the rates. If we actually look at what we got here in terms of potential energy surfaces close to crossing point, this is basically horizontal axis show reaction coordinates here, and vertical is energy basically in wave numbers. And the blue line and red lines that show interpolation of the reaction path basically, right? And the crossing point here marked again, minimum energy crossing point as an ECP. This is kind of like one-dimensional cross-section through 2 potential energy surfaces. In experiment, we actually have, turns out, which is haven't been known at that point. So what we actually in experiment, we in a tunneling regime. So we don't have enough energy to climb to minimum energy crossing point. So in fact, this is marked with this black horizontal line. You have ZPE plus 600 wave numbers. So this is how much energy basically dumped in the system optically. And therefore, the transition between triplet and singlet has to proceed through this sort of gray area over there, which is effectively the tunneling barrier, right? So, and the dashed line, by the way, represents simplest sort of interpolation based on Landau-Zener approximation, and the sort of blue and red curve show the actually more sophisticated Jun-Nakamura theory. So anyway, so it turns out you need tunneling basically to get from one state to another, in this case, to flip the spin. And the values we got here is, so again, experiment 23 nanosecond, Fermi-Golden rules is 0.02, 0.04, and we got 345. So we overestimate by about 1 order of magnitude, which is arguably better than underestimated by 3 order of magnitude. So, but at this point, we start looking why we're not getting more accurate numbers. And then we realize, well, we're treating, this is one-dimensional theory, so we're treating the tunneling as basically one-dimensional tunneling. So, and it's well known what the multidimensional effect in tunneling can be important, and in fact reduce the effective width of the barrier and so on. So the Don True have done a lot of work on this. And so we actually, in the conclusion of the paper, we wrote effectively what, well, we believe this is overestimated, the lifetime is overestimated due to the fact that we don't account for multidimensional character of the tunneling through the barrier. And then like about 2 years after this was, or a year and a half after this was published, so the paper came out by Jeremy Richardson from ETH. So, and they actually, because it's a small system, they were able to do the instanton theory on this. So we just much more sophisticated way to do that. And they basically use our electronic structure, the results effectively. So, and they show conclusively what, yes, that's multidimensional tunneling basically. And and in fact, they got the rate, I think, within like factor of 2 of experiment lifetime in this case. So, all right. So, I actually didn't look when I started. So how I'm doing on Okay, all right. So plenty of time here. So this is another example. So this is collaboration with the experimental group, surface science group. And the interest here is the basically they were looking at the hydrogen elimination desorption reaction of ethyl on silicon 100 surface. So this is, I mean, the functionalization of the superconducting surfaces are actually is kind of like very important things. So the industry interested in these things. And anyway, so the idea is again to look at the rates here of this reaction. And the reason we got interested is what turns out, and this is actually bringing me back to to my time in graduate school with Mark Gordon, where I heard all about the silicon surface and the diradical character of the silicon surface. So it turns out this dimers on silicon surface, they can have significant diradical character. They can be either open shell singlet or open shell triplet. And we got interested because, well, that means maybe there are some spin transitions from singlet to triplet basically occurred during the reaction. So we look at the several different this is several different reaction paths depending on, which also depends on the coverage, basically of the surface. And that's controlled by basically by pressure in the chamber and so on. So experimentally, this is what we found out for low coverage reactions. So here the black one is reaction path on singlet surface and red one on a triplet surface. So what's happening when you start from the left, from the reactants, you basically can go over the black barrier. That turns out, and I show on the next picture, actually doesn't actually agree with experiments. On the other hand, you can actually cross from black to the red one and go through the lower energy barrier, right? So, and proceeding to the same basically product at the end. So that's comparison with experiments and theory. And in experimental, so the this orange curve corresponds to high coverage, and that's actually reproduced by reaction path 1, 3, and 4. And that actually doesn't require any spin changes, so that's perfectly single state reaction paths. But for blue curve from experiments, which corresponds to low coverage, so if you look at the singlet-singlet reaction, basically, over the black barrier over there on the left, so that's produced, that's basically overestimates the temperature of the reaction by significant amount. So I think way over almost 200 kelvins or something like that. So, but if we're looking at the triplet barrier and assume the reaction proceeds through the spin forbidden path, so which means changing the spin state, so we actually have pretty good agreement with experiments. So we think this particular reaction does proceed through the spin forbidden channel basically, and which requires a change of the spin state from singlet to triplet. All right, so one more example here. So this is iron catalyzed CH bond activation. So CH bond activation obviously is very important in synthetic chemistry and in chemistry in general. So this is one of the critical steps to many reaction mechanisms. So the bond is relatively strong, about 110 kcal per mole. So therefore, to activate this bond, typically you need high temperature. So the work by Nakamura and co-author in 2008 actually made quite a splash basically in organic chemistry. So because they've metal organic chemistry, I guess. So they found out catalysts based on iron, which can effectively activate CH bond under 0 centigrade. So that's compared with typical reaction temperature in order of 100 centigrades for these reactions at least. So then came the work by Shaikh and coworkers. So they look at so that's not us. So they were the first one who look at the possibility of multi-state reactivity here, or two-state reactivity as they call it. So they propose quintet to singlet transitions. And that's, again, you can see red barrier significantly lower than the blue one. And that's why the reaction potentially can proceed at low temperature. The problem here, however, if you calculate spin orbit coupling between quintet and singlet, it's very close to 0. In fact, within first order perturbation theory, it's exactly 0, in fact. So, so that means, because probability of transition proportional to the square of spin orbit coupling, that means what this transitions from this blue to red curve is actually very unlikely to happen. So, so at this point, we start thinking about, well, what can happen maybe? So there is another state there is a triplet state, not just singlet and quintet. So the triplet state turns out to be in the middle between singlet and triplet, singlet and quintet, sorry. And when we look at this reaction path, we were able to find the minimum energy crossing points, 2 of them, MECP1 and MECP2 marked here, which have significant spin orbit coupling basically, because again, it's coupled the spin states which require only one flip of one electron spin instead of flipping 2 electron spin like for singlet quintet transition, right? So and in this case, so we believe what the reaction basically proceeds what we call multi-state reactivity, so which involve 3 states instead of 2 states proposed originally. So that's that's our sort of conclusion concerning this, and this is another application of this statistical theories, basically. So since John was talking about FMO, so there is a single slide here. So that's actually it's application. Basically, we implemented minimum energy crossing point search in FMO. So you need to find this minimum energy crossing point because that's what required for the calculating the rates, basically in statistical theory. So, and again, I am certainly not an expert in FMO. This is collaboration with Dmitry Fedorov in Japan and Yuri Alexeyev, who is basically senior computer scientist at Argonne National Lab. So, and the claim to fame here, we were able to run these things on something like 100,000 CPU cores, right? So, and it's actually scaled semi-reasonably. So we did the protein rubridoxin within the like this droplet of the water droplet, effectively. Like, I don't remember how many water molecules there. So now, again, so I'm not going to claim we learn anything useful out of that, but the point is we demonstrated the capability of basically running this type of calculation on supercomputers. So which is, so this is Mira supercomputer, so which is retired actually by now, last year, I think, or something like that. So now Aurora is coming. So I think in a month or something. I don't think it's operational yet. So anyway, so very quickly, last maybe 2 slides, so we'll see. So how hungry we are. So I talk about transition between different states in terms of like singlet, triplet, triplet, quintet, and so on. So, but one, of course, has to realize what these high-spin states, they contain multiple components with different MS quantum numbers. And everything I showed before, we basically use so-called effective approach to calculating spin-orbit coupling constant. And this is effectively the root mean square of the individual matrix elements of coupling between the different MS components, basically, of the spin states. And this is fine for most of the experiments because usually people measure the transitional rates or like lifetime of the excited states. But there are also emerging experiments where it is possible to look at specific population and the rate transition between specific MS components. So, and another motivation is what if you have external magnetic field, you have to think, because if magnetic field affect different MS component differently, you have to think about transition between specific MS components. So we recently implemented this sort of generalization of this NAST to look at the transition between specific MS components of the spin states, and on the right it's just again proof of concept. But the interesting thing, so actually the rates between transition of this is a singlet state and the MS plus minus 1 and singlet state and MS 0, and those rates can be very different. So in this case it's like 2 orders of magnitudes, right? So and they both quite different from effective rate. So, and in fact, you would think, so if you add those 2 rates, you get effective rate. Turns out it's only work if you use simple Landau-Zener for probability equation for probability of transition. So for more sophisticated, they're not actually transitional probability, they're not actually rates do not add exactly. So I'm going to skip that because I think we are running out of time. And in the summary, so I hope I show you what spin-dependent processes are important. So, and there are many examples. So excited states relaxation, spin-forbidden reaction, thermally activated. Molecular magnetism, I didn't talk about that here, but I mean, I mentioned that early on. So nonadiabatic statistical theory is complementary to MD. I'm not saying we shouldn't be using molecular dynamics. So nonadiabatic molecular dynamics is super useful for ultra-fast photochemical processes, for example. But for slow transitions between different spin states, you really want to use probably nonadiabatic statistical theory. It's also much more useful for large system. You can use accurate electronic structure methods, and we can relatively easily account for things like quantum effects like tunneling and zero-point vibrational energy. So I talk about several applications where we use different electronic structure method, anything from density functional theory to CASPT2 and a couple of clusters. So this is another sort of advantage of the statistical theory, because you don't need very many electronic structure calculation. You potentially can use very high level theory. And in the future, we're interested when we're kind of looking right now at the effect of magnetic field, and we're interested in controlling the spin transitions with external magnetic field. The code is online. So this is on the right, lower right corner. So The paper is published describing the code. The code is online. There are several people actually who used it already. So, and it seems to work. So the manual is relatively extensive. So if you want to try, so go ahead. And if there are any questions, please let me know. And at the end, this is my acknowledgement slide. This is the group on the right. On the left, people in the red boxes are the sort of main contributor to development of statistical theory. And I should acknowledge the funding from NSF and ACS Petroleum Research Fund. This is most of the funding for this work, but we also have large DOE grant I mentioned, but that's related to molecular magnets I didn't talk about today. So again, thank you for your attention.
Okay, let's have one or two questions from audience. And there is a question from the chat room. Yeah, a question from the chat room reads, a capacity to active space of 24 orbitals is enormous. How long did that simulation take? But my understanding is that there were 16 orbitals, right?
That's 24. I think it's 24 electrons, right? So
yeah, 24 electrons in 16 orbitals.
Yeah. Or something like that. Yeah, that's so yeah, that's not cheap. And by the way, we've done the geometry optimization with that. So, and Hessian calculation. Of course, this is tiny molecules, so we can do the it's basically numerical Hessian numerical. Well, actually for CASPT2, it's analytical gradient because we use MOPRO, so analytical gradient implemented there. But again, so this is simply because we don't do molecular dynamics, right? So we just optimizing the crossing point between two spin states, and we optimizing the two equilibrium structure for singlet and triplet state, right? So and because of that, we can afford this super expensive calculation. So I mean, to answer the question directly, I think it's like geometry optimization probably took about several days or something like that.
Yeah, Professor Trey.
Thanks very much for some powering. You kind of skipped the tunneling part, so maybe could you say more about it? Okay,
I really try to save the extra 2 minutes for lunch, but since you asked, so I can figure out how can I go back again. Okay, so here is. Oh, thank you. So so this is really this is for quantum tunneling. So this is we just playing with different ways to describe it. So the recoupling equation, this is what we use. Recoupling, and Zhima Kamura is not here, but that's what we use for the tire post-gen reaction. And this is right here. So Landau-Zeyer basically predict no tunneling, so because it's just Landau-Zeyer the way it's done, so it's only over the barrier. So, and here we just start playing with things like multiplying Landau-Zeyer by a cut tunneling and see what if we can get something similar to weak coupling, which is in this case is kind of like a reference. That's what you would be expecting, because weak coupling formula comes effectively with solution of one-dimensional Schrödinger equation. So I mean, there are some approximation. This is so-called WKB approximation, so semi-classical, but it's pretty close to the exact solution. What is really interesting here is the Fermi-Golden rule, so which is over there. So you're talking like 10 order of magnitude or something like that difference. So we I guess the main message here is what the Fermi-Golden rules can overestimate the rates and very far underestimate the lifetime by enormous amount. So in a way, the way I think about that is molecular dynamics is basically multi-dimensional theory. It's explore entire potential energy surface. So if you do MCTDH, you typically use several maybe vibrational modes, right? So but we do direct dynamics, we use basically all system, entire system. So anyway, so that's the entire system of many modes. When you go to Nonadiabatic statistical theory, which we use, so that's effectively one-dimensional theory, where the Fermi-Golden rule would be zero-dimensional theory, because you're only looking at the property at the minimum, basically, and there is no any information about reaction path there. So and that's why it does so badly.
I have a quick final question. Can you formulate some similar theory for the dynamics between the states with the same spin?
Oh yeah, sure. So the in fact the so where's a picture of this Ames propagation of the okay, so for example, here on the left, we have the sort of schematic of the propagating the Gaussians, right? So basis functions, nuclear basis function on two potential energy surfaces. So in this case, they mark as singlet and triplet. So, and you can see the crossing is just normal crossing, it's n minus dimensional crossing between the states. If you have states with the same spin, so if one of them ground state singlet, another one, for example, excited state singlet, you will have conical intersection between them. So the dimensionality of crossing sim will be n minus 2. And in fact, non-adiabatic dynamics, most of the non-adiabatic dynamics was originally developed to model the relaxation for conical intersections, so which were called internal conversions, right? So for the chemistry. So that's, in fact, this ab initio multiple spawning code that's originally developed by Todd Martinez for modeling the internal conversion, and we basically generalize it to intersystem crossing. So, and in fact, there are version now which can do both, so which is super useful. So you can do basically look at the for the chemistry where you have relaxation for both processes, which can be quite important actually.
Okay, let's thank Sergey again. And